Warm welcome to UppTalk Weekly, the Faculty of Science and Technology at Uppsala University popular science talk every Tuesday via Zoom. My name is Karin Tellenberg, and together with my colleagues Lina Sors Emilsson and Fredrik Engelman, we meet researchers and talk to them about current basic and applied research. Those of you who are with us live can, whenever you want, ask questions to today's guest. You write your questions in the chat and I will bring them into the conversation. Each UppTalk Weekly is also recorded and will be published afterwards at Uppsala University's YouTube channel and at UppTalk Weekly's website. Today we're going to talk about silicon nanosensors that can sense the world. Driven by continuous size downscaling, silicon chip technology has laid the foundation of our modern information society. But as we are approaching the limit on how small a chip can be, our guest today, Professor Zhen Zhang, is exploring silicon devices beyond size scaling directly as smart sensors that can sense the world. And these sensors have a wide range of potential applications, from hydrogen safety to rapid drug effect tests. Warm welcome, Zhen.
Okay, thank you, Karin, for the introduction, and good afternoon, everyone.
Yes, I think we can start with you giving a short presentation about yourself and why you chose the research area that you have chosen.
Yeah, so now I'm a professor in solid-state electronics at Uppsala University. I got my PhD in microelectronics from KTH in 2008. Then I joined IBM headquartered research, IBM TJ Watson Research Center, doing research on advanced silicon chip technology. Until 2013, when I got a Ingvar Carlsson Award from Sweden. Then I moved back to Sweden and started my research group in Uppsala. And why did I choose silicon technology? During my undergraduate study, I got my first PC and I got my first mobile phone. And for the first time, I used internet. And I did see and feel the fascinating change this new development had made to the society. And I also noticed that there was a common technical foundation behind all this new development. That was silicon technology. And that's why I so wanted to continue my study in this field. So that's why I chose the silicon technology. Yeah.
And what properties does silicon have that makes it such a useful material to work with?
Yeah. So first of all, the number one reason is that crystalline silicon is a semiconducting material. So its conductivity can be modulated by impurity doping, for example, impurity doping or apply an electric field. With this basic material property, it enabled the design of the most widely used silicon transistors as an efficient electronic switch, because we can use voltage to control the conductance of the device. By doing that, we can turn the on and off the current through the device, and the on and off states can be used to represent 1 and 0 in digital system. So this is widely used in almost every integrated digital circuit. So this is from a functionality point of view, why silicon is useful. And from process point of view, silicon is a unique material. So it's very easy to form electric insulator on silicon. We just need to do is to just oxidize silicon to form silicon oxide. So silicon oxide is an insulator, and it's very robust. It has a very good interface with silicon, and it can survive from high temperature annealing. and all kinds of chemical cleaning process, which is needed for the circuit fabrication. So this is, I think, from my own point of view, the availability of silicon oxide is enabled the large scale integration of silicon integrated circuits. So that's the second reason. And the third reason is that we all know that the silicon element is the second richest element in the Earth, and this guaranteed the materials availability with low cost, with low price, and we can purify silicon from sands with low cost. So these three reasons, I think, from my point of view, is the main reason why silicon is so useful.
Thank you. And apart from using silicon in chip for computers and mobile phones, you use silicon in solar cells as well due to these functions. But and this is something that a lot of people know about, but you are using silicon in another way and in sensors. Could you please tell us how you came up with that step to use silicon technology to develop sensors, and explain a bit about what a sensor is?
Yeah, that sounds good. It's a very good question. And this, in the past decades, the drastic development of silicon technology was mainly driven by device size downscaling, because the smaller the device size, the faster the operation speed, and the higher the integration density. And IBM just announced its 2 nanometer technology platform, which can integrate more than 50 billion transistors in a fingernail-sized silicon chip. And all these 50 billion transistors integrated in the chip they have to all function as expected. So this is really amazing achievement. And this silicon technology really created a powerful toolbox for device realization with extremely high precision. But on the other hand, we are basically approaching 2 nanometer dimension. 2 nanometer, just a few times the atom distance in the silicon lattice. And that means that the scaling is really approaching its fundamental physical limit. And as a researcher in this field, we have to think of how to move forward with the powerful silicon technology toolbox. And what we decided to do is to use that toolbox to explore silicon devices directly as smart sensors to sense the world. And why sensors then? Because in our digital society, almost everything is connected via internet. And all the information input from the real world to the digital world is converted from all kinds of different sensors. So sensor is very important device for our daily life. Then if you look at our mobile phone, so there are I just checked, more than 20 different type of electronic sensors integrated in the mobile phone to convert our different daily events to digital data. So it's very useful, important devices for the future. And why silicon then? Why silicon device then? Because number one, silicon is a very special material. It has very high sensitivity to the change of many different physical parameters. For example, the light intensity, the temperature, the electric field, mechanical force. Basically, it's a special material. It's basically very good for sensing application. And with device size downscaling, we can make the sensor very small, which can achieve very high volume, very big volume, surface to volume ratio. The surface can be used to collect the changes in outside, right? So the big surface area, we collect as much change as needed, then and use that change to modulate the carrier transport in tiny volume. So this big surface to volume ratio can really benefit the signal generation. And that's why first reason why silicon. The second one is the third one. That's the second one. The third one is that with device size downscaling, we can use the tiny sensor to handle really small amount of sample. So which is very important for some applications. For example, if we want to analyze sample from some patient, and sometimes it's very demanding to get a sufficient amount of samples from the patient. So this small sensor will help that. And with, in addition with the large scale integration, we can integrate many silicon sensors in a sensor chip to perform multiplexed analysis, which can greatly enhance the efficiency of analysis and reduce analysis time. And finally, if we use silicon sensors, this silicon sensor chip can be manufactured in the well-established silicon manufacturing foundry to make a mass production with low cost. Yeah, so this is why sensors and why silicon devices for sensing.
Yes, we have got a question from Mikael. Yeah. Billion transistors on one chip. How many transistors are produced per day in the world? Do you know that?
That it's very hard to predict.
Yeah. It must be a lot.
Yeah, it must be a lot.
Yeah, and we have a following up question. 2 nanometer platform, how small can you get physically? Are there alternatives to silicon to make much smaller components?
No, I think now it's already really approaching the limit. Actually, industry is not really shrink the size, and actually they are exploring the third dimension, because in the old traditional way of integration, we just make the device in the planar surface. But now for example, IBM 2 nanometer technology, they are extending the vertical direction to lay out transistors on top of each other to reduce the effective size of the transistor. So basically, they are not like really make the real size smaller. Actually, they are making the effective size smaller by exploring the third dimension.
Thank you. If we go back to the sensors, you've started to explain a bit, and I've read about that. It's been explained like you're putting a small lab on this chip with the sensors. Could you? I know that you have compared how the sensor work with how the air works. So could you just give us an example, illustration about how the sensors works?
Yeah, actually the almost all the silicon devices, they are dealing with charges. So basically by nature, they are very sensitive to the charge amount change or charge distribution change around it. So if we want to use these silicon devices to sense a target analyte, and what we need to do is to make some special configuration so that the device can have specific interaction with the target analyte. And this can be realized by, for example, coat a well-designed sensing layer to coat it on the sensor surface. The sensing layer will generate specific interaction with the target analyte. So this specific interaction between the target and the sensor will change either charge amount or charge distribution on the sensor surface. Then the sensor will sense that and convert it to a current change. So that is a basic principle how like we design the sensor. But this is very abstractive. We can take our ear as example, as an analogy to further understand this. Because our ear is a sound sensor. Basically, it can detect sounds. But we are using that every day to sense the world with many different kinds of purpose. And if we sit in a dark room, and we can use our ear to sense if there is mosquitoes or flies, and we can differentiate mosquitoes and flies with just by the ear detection of sounds. This is just a common practice that how we use our ear. But if we can make some special design, we can even use our ears to detect the fishes in the lake. What we need to do to achieve that purpose is that we can make a fish net and put it in the lake, then connect the fish net to a bell. So with the fish net, captured some fish, and the fish will shake the fish net and ring the bell. Then we know that the fish is captured in the fish net. So this basically the fish net and the bell is basically the special configuration, bring together the fish and the ear, to hook up the connection between the fish and the ear. Of course, in the real design, you know, in the real electronic sensor design, this in the sensing environment, there's always some like non-specific interaction. For example, take the ear as example. The wind around the lake can also shake, can ring the bell, right? And generate false signal, then cheat you. And to avoid this, to be cheated by the wind signal, I can come up with two strategies. One is that we can make a very tight, very strong connection between the fish net and the bell, and to make sure that any fish captured by fish net, it will ring the bell much stronger than the wind can do. If we can achieve that, we don't need to care about the little noise generated by the wind. But if we cannot achieve that, and we have a backup solution, is that we completely prevent the wind to interact with the bell by create a solid fence surrounding the bell, so the wind cannot reach the bell. So this is like how we can make sure that we can sense something that we really want to sense. But in reality, to make such a design in real electronic sensor is not as easy as like the fish net case, because we know exactly how the fish net will interact with fish and with bell and with ear. And to make guarantee a specific detection of something with electronic sensor, this part is still the most challenging part in the sensor development. And to achieve that, we need a very deep understanding on how the electronic sensors is interacting with different species in the sensing environment. We have to achieve this type of understanding before we can make a correct configuration to enhance the signal and then minimize noise or interference. And in the past years, we have spent most of our time to reach such a type of understanding. And this cannot, could not be achieved by a single research group. This requires a wide, very broad range of knowledge. We have to collaborate with professors in electrochemistry, in biochemistry, in physics to get such kind of understanding. So now we have created a pretty good platform to making sensors for sensor fabrication. We have achieved the pretty deep understanding on how electronic sensors with the environment. So that's why we are now trying to standing from here to explore real applications. Yeah.
Thank you very much for this very good explanation. And as you said, you can use it in different applications. And I mentioned in the introduction, it was hydrogen safety and rapid drug effect tests. Could you tell us a bit about how this works with these sensors? If you go to hydrogen safety, for example.
Yeah, so because hydrogen society is now being promoted by many countries because hydrogen is a clean fuel. And if we burn hydrogen, it will release energy and the end product will be water. It does not generate any pollution. And Sweden is talking about converting the ferry from Nynäshamn to Gotland with hydrogen-driven ferry. And the Toyota company is selling hydrogen cars. But hydrogen is very dangerous gas because it could be very explosive. Since if you have a hydrogen leak to the air, if the volume percentage is over 4%, it can be very dangerous. You can think of if you have many hydrogen cars parked in the underground garage, if any car is leaking without a good hydrogen leaking detector, it can be very, very dangerous to the building or to the people living in the building. And with the nanoscale silicon device, we can basically create a good device design to make a tight connection between the hydrogen presence to the electrostatics in the silicon channel. So basically, with a new device design we just managed, we can make a much stronger connection between the hydrogen presence to the signal generation. We can produce like a many times larger signal than the traditional silicon sensor, traditional electronic sensors to detect hydrogen. So this is the one project we are working on. And we can also use the nanosensor to precisely detect the metabolic product released by bacteria. So if we have an infection, you really want to know which drug can effectively kill the bacteria. And by using this device, we can make a real-time monitoring on the metabolic profile of the bacteria under different antibiotic treatment. From that profiling, we can very quickly tell which drug can effectively kill the bacteria within 30 minutes. And in addition to that, because our sensor is really small, so the amount of bacteria that is needed to start the testing is very little. So we can say if we use this sensor to start their test, we save a lot of sample preparation time also. So these are the two applications we are working on.
Yes, and we have a question here from Xian. Are nanosensors related to biosensors?
Yeah, this is a type of biosensor. The antibiotic resistant testing one is a biosensor we are working on.
And we have another question from Mikael. What do you need to produce the sensors you describe? It does not sound as you can do it in your office, equipment and infrastructure and more.
Yes, that's a good question. Actually, as we talk about before, that the device or sensor we are dealing with is in the nanometer range. And how small it is, I can give you a good reference. Our hair, the human hair, the diameter of the hair, the size is about tens of microns. And our sensor size is about 10 nanometers, which means the size of the sensor is about more than 1,000 times smaller than the diameter of the hair. And to fabricate these devices, we need a very advanced lab with almost no dust, no vibration, and no temperature drift, because most of the dust, their size is like tens or 100 times larger than the device we are making. One dust can destroy many devices in the chip. And also the environment vibration probably in the range of a micrometer. It's also many times larger than the size we are dealing with. And if you have like a vibration in the fabrication table, so it can destroy all the resolution we want to achieve. And also all the big machines that is used for the device fabrication, they are controlled by electronics, and the electronics has very strong dependence on the temperature variation. If the temperature is drifting and all the machine, their characteristics is drifting, then we will not achieve, if that happens, we will not achieve the resolution we want. So basically we need a very advanced lab with almost no dust, no vibration, and no temperature drift. And for some of the part in our clean room lab in this building, and we have to suspend the whole lab from the environment. So the whole lab is suspended. So when the car is running around, it will generate vibration to the lab. Yeah.
Interesting. Is there any other applications that you are working on apart from hydrogen safety and this rapid drug tests? Maybe not now, but do you have something for the future that you really want to explore when it comes to these sensors?
Yeah, so there's one big project we are running, a voluntary project we are running, is that we are taking advantage of the high precision fabrication capability of silicon technology. We are creating a really, really small silicon-based reaction chamber, which is the volume of the chamber is 10 to minus 18 liter. We are trying to electrically drive single molecules into this tiny chamber with good controllability, then study single molecule interactions inside this really extremely confined volume. Since in most of the living biosystem, the molecular interactions happens in extremely confined space. Hopefully, the development of these this tiny reaction chamber can facilitate our understanding on living biosystem at a single molecule level. This is a long-term project. We are still working on it. So this is something I want to bring up.
Yeah, and I think you mentioned it, but as we're down on single molecule level, it must be really, really, really hard to understand what these sensors are picking up. And as you said in the drug tests, to see antibiotics and how to kill a bacteria, it's only about the ions. This is something that you have to work a lot with too. And if you compare it to the ear, you must know if it's the fish that rings the bell.
Yeah.
How do you do that? How do you work with knowing what the sensors are picking up so that you can make the right decision?
So basically, we know what we, in this case, we know what we have loaded in the reaction chamber. We know what, if a molecule interacts, we know what kind of product we make. So for example, if some interactions we release hydrogen ions, we can integrate a hydrogen ion detector in the chamber to detect the interaction product, the reaction products. So this is something still ongoing. I think we are at the #1 step. We are trying to controllably load single molecules into this tiny chamber now. So that when we may manage that, the next step is that how we can design integrated sensor to really sense the single molecule interactions inside the chamber. Yeah.
And we have another question: how to speed up and make it cheaper with your kind of sensors for DNA sequencing?
Yeah, actually, there's this a on-chip silicon chip-based DNA sequencing tool already developed, is commercially available. And yeah, I think we are not working on that type of technology, but there's a commercially available tools based on silicon chip technology. Yeah.
We're approaching half an hour. I have the last question. Is there something that you want to tell our audience that we haven't really talked about when it comes to your research about these sensors?
Yeah, actually, I think we have established good fabrication device platform, and we have achieved a pretty good understanding how the device can interact with the environment. And we think these can solve a lot of good scientific questions, answers a lot of good scientific questions. We are actively looking for collaborators from different areas to bring up high quality questions to attack using our sensors. And we also already filed a few patents based on what you mentioned. We are also trying to collaborate with industry partner to commercialize these ideas, and this is what we are also actively looking for. Basically, so utilization of the technology.
Yeah. So when do you think that these things that you're working with will be out on the market? Do you have any idea?
It's very hard to predict.
Yeah.
Yeah. This is very hard to predict. I don't want to make a too big promise on this.
Yeah. Well, we hope that they're out there soon. Thank you very much, Zhen, for joining us today and talking about this interesting but kind of hard to understand subject. But I think that you managed very well to put it down on popular science level. So thank you very much for this.
Thank you very much. Thank you. Thank you.
Next UppTalk Weekly will be on February 28th, so not next week, but the week after that. And then we will meet Cecilia Persson, and we will talk about 3D printed material that can make the body heal itself. So thank you very much for today, and see you in 2 weeks.